Hello, Flat Earth researchers, debaters, and debunkers. The way we see the stars appear in the sky at any given location on the Earth are often cited as proof that we live on a rotating globe. Now, there's no denying that you can quite accurately determine your latitude on the Earth if you look at Polaris and see the height or the altitude that it appears above the horizon. And of course, it's assumed that when you get as far as the equator and Polaris is down on the horizon, or then you go beyond the equator and you can't see Polaris anymore, that this is because you're on the outside of a spinning globe. But let's look at what we really see here and compare it to how we see things on the Earth in the real world, and see if we can interpret it in a different way other than this assumption that we're on a rotating spherical Earth. As I said, there's no denying that it works. Celestial navigation is at the root of how we get around the Earth. It doesn't really work for longitude, but we can determine our latitude, or the distance that we are from the assumed North Pole, depending on how high above the horizon we see Polaris. Personally, I've never seen a photograph of someone at the North Pole looking directly up at Polaris, so who knows where it really is in the sky. But yes, you can get very accurate readings for the altitude of Polaris in the sky to find out where you are on a map of the Earth, whether that's a flat or a spherical Earth map. It doesn't really make any difference. Of course, when it comes to determining your longitude, that's when you have to take time into consideration. So the latitude, or our distance from the North Pole, is based on these celestial observations, whereas our longitude, which direction we are from the North Pole, is determined by time. So these are two very different aspects of navigation which come together to give us this representation of a globe. But we can look at the stars, and with the globe model, we have to assume that each star is millions of miles away from us, and they are each millions of miles away from each other. But is that really true? That seems to me just to be an assumption, or a necessary assumption for the globe, because when we see the stars go across the sky, we don't see much change in terms of parallax. But without making any assumptions or trying to explain what I think the stars are, let's just look at what we see here when we have a photograph that has Polaris near the top here of this photograph, and then all these other stars around it, and we see these longer and longer star trails as they come down towards the bottom of the photograph on the right and the left here. So does this really tell us we are living on a globe, or does it tell us something else? Can we interpret it in a different way? Let's go and have a look at some pictures that we can make assumptions about in real life on the Earth. So when we look at a scene like this and we talk about it in terms of perspective, we instinctively know several things about what we can see here. We know that this ship down here is in the foreground, and it is closer to us than the other ships. And we also have some aircraft here which we can tell that are somewhere pretty much above this ship in the foreground. They might be a bit further away, but we've got an idea of their relative height and position relative to this ship in the foreground. Then we've got two other ships which appear to be physically larger than the one in the foreground, but of course they appear smaller because they are further away. And we know they are further away because they are more up towards the horizon across the level surface that we can see here. And of course, the third ship is even further away than that second one. So we instinctively know this, and as you know, we can also get an idea of the distance between the ship in the foreground and the second one. And now there might be an equal distance between this second ship in the middle and the one that's further away, but just because of our height above the surface, the distance here between these two appears more condensed. You know, this again is all to do with perspective and where we actually are. It's always going to be subjective, but we know that the further away we can see into the distance, the more condensed everything becomes on the surface. Up here on the top right, there's another ship or boat over here. So of course, because it's so far away, it's difficult to tell exactly how large it is or what kind of ship it is. But again, we know that it's far away because it's gone much closer to the horizon across the surface there, and of course it's much smaller. So what we can do here is we can add some markers to indicate what we're seeing here. So for example, in the foreground here, the distance that we can see in this reference frame across the foreground, let's say for the sake of argument, is 1 kilometer across. So if this boat traveled across this field of view, it might cover about 1 kilometer. And so we know that for the apparent distance across for 1 kilometer further away will obviously appear to be shorter. So a boat travelling across this scene for 1 kilometre will appear to cover a much shorter distance across our field of view than one in the foreground. And of course, a boat closer to the horizon will travel 1 kilometre, but it will appear to have hardly moved across the horizon. So of course, by the time we are looking across this horizon at the top here, we are covering maybe tens of kilometers, whereas down here our view across the scene is about 1 kilometer. So of course, again, the further that we see into the distance, the greater distance across we are seeing. This is one of those aspects of curvature where you can assume that you're seeing a ship go down across a curve, down a curve in front of you, but then you take that same distance across and we never see any kind of curvature. So this in itself is just one of those comparisons we can make if you're talking in terms of scientific exploration and measurement. If you're claiming to see a ship drop off the horizon and go down a curve in front of you at a certain number of kilometers, then of course we should see the same thing happening across a very wide field of view. Anyway, I digress. I'm sure you get the point by now that the closer something is to us in our field of view, the quicker it will travel across from one side of the other of our field of view. And the further away something is, the shorter distance it will cover in our field of view. That's just something we instinctively know. It's a common sense observation of reality. So that's what we can see in reality. So let's go back and compare it to what we're seeing with the star trails here. And as I mentioned earlier on, these ones down on the right here appear to have these longer streaks or trails than the ones that are essentially further away, and they get closer to Polaris. So it appears what we're seeing here, I've just put these, you can see these green lines I've put as an example. So keeping in mind that whatever is turning, and whatever we can say is turning at 15 degrees per hour, what we see here as a result of perspective is these trails here, which appear to be much closer to us, as we saw with the close ship, cover more distance in the photograph, in our field of view, than those that are more towards the center, or the center of this spiral or trail or Polaris. Here we can assume that they are covering the same distance at the same speed, because everything appears to be rotating at the same speed, yet here it's a shorter trail and they get shorter and shorter. So from our own instinctive common sense observations of reality, we can infer and interpret what we see here as being as stars that are very close to us here, and Polaris, which is hardly moving, is further away. Now that has nothing to do with the shape of the Earth beneath our feet. This has to do with what we are actually looking at in the sky. We appear to be looking at this tunnel. And if you have a look down here to the right, where we've got whatever stars these are coming down and almost hitting the ground here, again, this is in terms of perspective. We know that if we moved forwards here, let's say we moved northwards from this position, these stars that we see in the lower part of our field of view would, of course, become higher in the field of view. So you can see from this that there are no stars going under the Earth or being blocked by any Earth. They're all going on up in the sky here. Okay, so this, we're not, this can be a level surface. We move to the north on the level surface and we would see more of these lower star trails. They're not getting blocked up by any rotating Earth. Let's have a look at another photograph here. So this is, you can see here that on the left here we have these long star trails, and they get shorter and shorter and shorter as they get off to this center point over here. Again, the photographer wasn't pointing at Polaris, but we can see that off to the right, as these stars get closer to their pole star, then of course they cover shorter and shorter distances, and over here. So we can assume that these stars here are very close to us, the ones that are making these long trails, and the shorter ones are getting further away from us, regardless of the actual shape of the Earth. Again, it kind of looks weird. They don't really match each other. They certainly don't. The land and what we see in the sky doesn't match as being on a globe and having these stars go around us. Let's have a look at another one. So what I wanted to point out with this particular image is this seems to be looking more upwards, so straight up at stars as they cross the sky. And of course here we are seeing the lengths of these lines across our field of view are really quite similar, because it's focused in on this spot of sky which is obviously pretty much directly above the observer here, or the photographer. Here we can see a similar thing going on, where we're not seeing this spiraling or going towards a center point, because the photographer is looking directly up at some stars here, and they are going across the field of view. So all the stars that are close by, just going across the field of view, have a very similar trail length in the photograph, because we're not having this expanded view of the whole sky. Whereas here, I think this is a fantastic photograph. Polaris is lower than it appeared in that other one, but look at these stars here. So all these stars, we have this kind of tunnel effect. And again, this doesn't dictate in any way that we are on a globe. All this appears to be happening above the Earth. It's like the stars are a tunnel in the sky that's going on above us, and they never go underneath us. You can see these trails here on the right hand side. It would come down and hit the horizon, but we know that, again, this is just a result of perspective. The same for these trails on the left. They are longer, so they are closer. So these ones are closer to us, and Polaris and the ones closer to it are much, much further away. But they're not further away to. Do you see? If we're on the outside of a globe, that's not going out. It's not going towards the top of the globe. This is up. This is literally up in the sky. It's not towards some North Pole. Okay. Yes, if we moved north and we headed towards Polaris, it would come higher up in our field of view on this image. But so would everything else. It doesn't mean that we're on a globe. Yeah, it's just the spherical geometry of perspective that can be used to describe perspective is converted into this idea that we live on a globe. So this again really shows this tunnel-like effect. And again, we can see all these stars, all these stars above Polaris doing these circuits, however they would do them at night. Yeah, well, they will do a full circle, and they'll only be obstructed by whatever's on the surface of the Earth. They're not obstructed by any curvature. It's not because we're on a sphere. We can simply assume from our observation that these long trails here are closer to us, and it's all moving. This is all moving in one big, whatever it is, dark matter tunnel. So talking of tunnels, let's just have a look at how tunnels look. Here's an example of that, where we just, again, see exactly the same aspects of perspective. In fact, what might be fun to do is to turn this around. If we can do this, okay, rotate, whoop, and this looks very similar to this, doesn't it? Yeah, we've got this. We're looking up towards something far away, above us. Yeah, I think it's fantastic representation. It's how we see the world. Yeah, you can imagine these star trails here, part of this tunnel wall. So of course, the further we see along the tunnel, the shorter that same distance will appear, until we've got these the tunnel walls arcing all the way across our field of view here. But in the distance, the same amount of tunnel wall is just arcing across a very small portion. Some more examples. And this is another wonderful example of perspective. And even at this short distance, we can see that these lights in the ceiling will eventually appear to converge. And any movement going on up there would be almost invisible compared to what's going on down here in the foreground. It's fantastic. So that's what I see when I look at these star trails. I see some kind of tunnel of everything moving, and in many senses, why not? Because we have to have this movement for time. Without movement, you have no time. And this is the esoteric nature of where we live. We don't know what the stars are. We don't know what's really going on in the sky, but we know that it is intrinsic and essential to our life on this earth. And it's used as a clock. The big clock in the sky, telling the time. All right, so as always, perspective is the imaginary curve. Thank you very much.